In 1982, two physicists published a paper that quietly broke the most famous experiment in all of physics, and almost nobody noticed. For 40 years before that, the story of the double slit experiment had been simple and a little spooky and deeply comforting. A particle behaves like a wave when nobody is watching, and like a particle when somebody is, and so reality somehow responds to being observed. You look, and the universe changes. That is the version in every textbook, on every science channel, and it is the version that made us feel important because it put human awareness at the center of everything. But underneath that story, there is a second layer, confirmed and reconfirmed in laboratories on 5 continents. And the second layer does not care about you. It does not care about consciousness. In 2012, a machine with no more awareness than a light switch made the choice, and reality obeyed it just the same. So here is the question we're going to follow tonight, all the way down. If the universe is not responding to a mind, then what exactly is it responding to? Get comfortable. Subscribe if you have not, and stay with us, because the answer reaches back 220 years to a sunbeam and a thin card, and forward to a mystery physics still cannot solve. Let us get into it. Part 1. The version you were taught. You already know about the double slit experiment, or you think you do, and the gap between those two things, between the version you were taught and the version that is actually true, is what tonight is about. Here is the version you know. A particle is fired at a barrier. The barrier has 2 slits cut into it. Behind the barrier sits a detector, a screen, something that records where the particle lands. And when you run the experiment without checking which slit the particle passes through, the particles do not pile up in 2 neat clusters the way you would expect from anything sensible, anything bullet-like. They arrange themselves into an interference pattern. Bright bands and dark bands, alternating the unmistakable signature of waves. But the moment you place a detector at the slits, a device that records which slit each particle actually went through, the pattern collapses. The bands vanish. You get 2 clusters, exactly what you would expect from particles behaving like tiny projectiles. Observation collapses the wave function. You look, and reality changes. That is the story. It is on every popular science channel. It is in every physics textbook written for a general audience in the last 40 years. And here is the uncomfortable thing I need to tell you before we go any further. It is not wrong exactly, but it is incomplete in a way that should genuinely disturb you. Because starting in 1982 and accelerating through a series of experiments that most people have never heard of, physicists discovered a second layer underneath that familiar story, a second layer that has been sitting in the scientific journals for over 40 years, confirmed and reconfirmed across multiple laboratories on multiple continents, and almost entirely absent from the version of this experiment you have ever been told. And the second layer does not care about you. Let me be precise about what I mean by that, because I do not mean it the way it sounds. The second layer does not care about consciousness. It does not care about awareness. It does not care whether anything watching the experiment is alive or aware, or has any capacity for experience whatsoever. In 2012, a team of physicists in Vienna ran a version of this experiment in which the choice of whether to record information about the particle's path was made not by a person, but by a machine, a quantum random number generator, a device sampling random noise with no human being anywhere in the decision, and the results were identical. The pattern still changed. The particle's behavior still reorganized itself perfectly around a choice made by something with no more awareness than a light switch. And the part of this that should keep you up tonight, the part that the comfortable version carefully leaves out, is not that reality responds to observation. It is that reality responds to something else entirely. Something that is not a mind. Something that physicists, as of right now in 2026, cannot define, cannot fully explain, and cannot agree on. The double slit experiment has a second layer, and the second layer is worse than the first. I want you to hold on to that phrase because we are going to come back to it. The second layer is worse than the first. By the end of tonight, you are going to understand exactly what that word, worse, really means. And I will tell you now, gently, so it does not startle you later, that it does not mean frightening. It means something stranger than that. But to understand why the second layer is worse, you need to see the first layer clearly. Not the simplified version, not the cartoon version with a little ball rolling through two doorways, the actual experiments, the actual apparatus, the actual people who built that apparatus with their own hands and what the work cost them. Because this is not really a story about an abstraction from a textbook. It is a story about a small number of human beings, spread across 2 centuries, each of whom looked very carefully at something very small, and each of whom found the same thing waiting for them. And it is a story about how the rest of the world responded to what they found. And that story does not begin with quantum mechanics. It does not begin with particles at all. It begins with a beam of sunlight, a thin card held edgewise, and a man whose discovery was so threatening to the scientific establishment of his time that they buried it for more than a decade. So let us start there. Let us start in a room in London in the year 1803, with the most gifted human being most people have never heard of. And one last thing before we begin, because I want you to know what kind of journey this is going to be. This is not a story with a villain, and it is not a story with a tidy ending. It is a story about a question that has been getting slowly, patiently sharper for 220 years, and about the handful of people who built the machines that sharpened it, and about what those machines have shown us, and about the one thing, the final thing, that even now, even tonight, nobody can explain. So settle in. Let the names and the dates wash over you. You do not need to hold on to every detail. You only need to follow the thread, because the thread runs all the way through, from a sunbeam in London to a question physics still cannot answer, and it is a thread worth following to the end. Part 2. Thomas Young and the Sunbeam. Thomas Young was born in 1773 in Milverton, a small town in Somerset, England, into a Quaker merchant family, and by any reasonable standard, he was one of the most gifted human beings who has ever lived. I do not say that for effect. I say it because the record is genuinely difficult to believe. Young could read fluently by the age of 2. He had read the entire Bible through, twice before his 5th birthday. By his teenage years, he had studied 13 languages, and not easy ones, not languages closely related to his own: Arabic, Persian, Turkish, Ethiopic. He went on to earn a medical degree from the University of Göttingen in 1796, and he became a Fellow of the Royal Society, the most prestigious scientific body in Britain, at the age of 21. Over his life, he made foundational contributions to optics, to the physics of elasticity, to the science of colour vision, to Egyptology, and to linguistics. Cambridge students gave him a nickname. They called him Phenomenon Young, and from what we can tell, they meant it as both a compliment and a quiet warning. In 1801, Young was appointed Professor of Natural Philosophy at the Royal Institution in London, where over the course of 2 years he delivered 91 lectures. And it was during this period of his life that he performed an experiment so elegant that, 2 centuries later, in the year 2002, the readers of a major physics magazine would vote it the most beautiful experiment in all of physics. Now here is where I need you to pay close attention, because the modern textbook version of what Young did gets it wrong, and it gets it wrong in a way that quietly obscures the entire point. The textbooks will tell you Young cut 2 slits into a screen. He did not. What he actually did was both simpler and in a way more clever than that. He took a beam of sunlight, directed through a small hole using a steering mirror to make the beam narrow and controlled, and then, into the path of that single beam, he placed a thin card, held edgewise, a card on its edge, splitting the beam into 2. The light bent around either side of that card. The 2 portions of light spread, overlapped on the far wall, and where they overlapped they produced something. Alternating bands, bright then dark, then bright, then dark. Interference fringes, the same pattern you have seen in the sheen of an oil slick on a wet road, the same colours that swim across the surface of a soap bubble, and then Young performed the step that mattered most, the step that turned a pretty effect into a proof. He took a second card and he pushed it slowly into the path of the light, until it blocked one of the 2 beams, just one, and when he did that, the fringes vanished. Not just on one side, on both sides. The entire pattern collapsed, because the pattern had never belonged to either beam alone. It required both. It was something that happened between them, and the only thing in nature that does that interferes with itself in that particular way, is a wave. Young had shown, with a sunbeam and 2 pieces of card, that light is a wave. He presented the result in 1803 in what was called the Bakerian lecture, delivered to the Royal Society, and it was published the following year in the Society's journal. Young described his finding as so simple and so demonstrative, a proof of the wave nature of light that he expected it to settle the question once and for all. The debate had been running for over a century. Was light made of waves, or was it made of particles? Young believed he had just ended that debate. He had not ended anything. What he had actually done, though he did not know it yet, was put his own career in serious danger, because Isaac Newton, a century earlier, had said light was made of particles. And in the England of 1803, Newton was not merely a respected scientist. Newton was sacred. To produce evidence that contradicted Newton was, in the eyes of a certain part of the establishment, not science. It was something closer to heresy. A man named Henry Brougham, a co-founder of an influential journal called the Edinburgh Review, and a devoted follower of Newton's particle theory, launched a series of anonymous attacks on Young's work. And those attacks were vicious, even by the rough standards of the era. Brougham wrote that Young's paper contained nothing that deserved to be called either an experiment or a discovery. He wrote that it was destitute of every species of merit. He set out, in print and in secret, to destroy the reputation of the most learned man in Britain, and it worked. That is the part that should sit uneasily with you. It worked. Historians describe Young's optical research as sinking into virtual oblivion in the years that followed. Young, wounded, eventually stepped away from the study of light almost entirely. He turned to Egyptology, to his medical practice. He resolved that any future work he published outside of medicine would be published anonymously, so that it could not be attacked the way his light experiment had been. The wave theory of light would not be properly vindicated for more than a decade, and when it was, the vindication would come from France, from other men, Augustin Fresnel and François Arago, building the case again from the beginning. Young died in 1829. His monument in Westminster Abbey describes him as a man alike eminent in almost every department of human learning. And I want you to sit with what actually happened to him, because it is a pattern, and the pattern is going to repeat through this entire story. A man performed an experiment that revealed something true and fundamental about the nature of reality, and the establishment of his time did not bury that experiment because it was wrong. They did not bury it because the evidence was weak or ambiguous. They buried it because the implication was uncomfortable. The evidence said that what everyone believed about light was incomplete, and rather than update the belief, the establishment attacked the person who had brought them the evidence. Hold that thought, because here is something I want you to carry all the way to the end of tonight. The experiment Young performed never changed. The sunbeam, the card, the fringes on the wall, all of it was exactly as true in 1803 as it is right now. What changed slowly, painfully, over decades, was not the experiment. It was our ability to hear what the experiment was telling us. The experiment never changed, only our ability to hear it. That is going to matter more than you might think. Because the next person to look very carefully at this same effect would not be looking at sunlight. He would be looking at matter itself, at particles with mass and charge and weight. And he would do it not in a grand lecture hall at the Royal Institution, but alone, late at night, in a basement, with apparatus he had to build with his own hands because the tools he needed did not yet exist anywhere in the world. Part 3. Jönsson. In the basement. For more than 150 years after Young, the double-slit experiment with actual particles of matter rather than light existed only as a thought experiment. Physicists would describe it. They would write it on chalkboards. They would say, imagine you could fire electrons one at a time through two slits. And then they would add, almost as a reflex, but of course you could never actually do this. The slits would have to be impossibly narrow, the apparatus impossibly precise. It was a beautiful idea that everyone agreed belonged permanently in the realm of imagination. Claus Jönsson did not agree. Jansen was a doctoral student at the University of Tübingen in Germany, and at the end of the 1950s he set out to do the thing everyone said could not be done. To take an electron, a particle of matter with measurable mass and measurable electric charge, and send it through a genuine double slit, and see what it did. And when I tell you he performed this experiment, I want you to understand what that sentence actually contains. It contains years of one young man's life. Because the technology to do what Jansen needed simply did not exist. So before he could run the experiment, he had to build the tools to run the experiment. He had to invent his way to the starting line. Consider just one piece of it, the slits. The slits had to be cut into a thin sheet of metal, into copper foil, and they had to be approximately 300 nanometers wide. I want to give you a way to feel how small that is, because the number alone will not do it. A human hair is roughly 75,000 nanometers across. Jansen's slits were around 300. That means each slit was something like 250 times narrower than a single strand of human hair. He was not cutting a slot you could see, he was cutting a slot you could not see into metal, using electron beam irradiation on silver-coated glass plates by hand, working largely alone, through long nights in a university basement. His supervisor was a physicist named Gottfried Müllenstedt, a man so accomplished in his field that colleagues had given him an almost mythic nickname. They called him the German Pope of electron microscopy. Müllenstedt had, a few years earlier, invented a device called the electron biprism, an instrument that could split a beam of electrons much the way Young's thin card had split a beam of light. And Jansen's project, the thing Müllenstedt set him toward, was to push that work further, to do, with electrons, with matter, what Young had done with sunlight a century and a half before. I want to take you into that basement for a moment. Not the textbook version, the actual room. It is late. The university above you is empty and quiet, the kind of quiet that has a sound to it. You're bent over a workbench under a single hard light, and you have been here for hours, and you have been here for hours on many nights before this one. In front of you is the apparatus you have spent a significant portion of your young life building. The copper foil with its slits, each one finer than anything you could see with your eyes, sits inside a vacuum. You have an electron source, a way to fire a controlled stream of electrons toward that foil, and behind it, a detector, a surface that will record where the electrons land. You have checked everything. You have checked everything more times than you can count, and now you simply run it, and you wait, and you look at the detector, and there, slowly emerging on the surface, are bands. Bright bands and dark bands, stripes, interference fringes, the exact pattern Thomas Young saw on his wall in London, except that you are not looking at light. You are looking at electrons. You are looking at matter behaving as a wave. You turn, and you call out to the only other person still in the building, a fellow doctoral student named Dietrich, working late down the corridor. He comes, he looks, and in the local Swabian dialect, almost involuntarily he says it out loud. There they are, the stripes. That moment, in 1959, 2 graduate students alone in a basement, was one of the most important moments in the history of quantum mechanics. Jansen published the results in 1961 in a German physics journal. And here is the part that should make you angry. In the same quiet way the Thomas Young story should have made you angry. An English translation of Jansen's paper did not appear for 13 years. 13! The single most important demonstration experiment in the history of quantum mechanics, the one that proved the most famous thought experiment in physics was physically actually real, sat in a German-language journal, largely unread by the wide world, for over a decade. When the English translation finally appeared, in 1974, in an American physics journal, the editor attached a note. And the note observed, almost wearily, that for decades the 2-slit electron experiment had been presented as a thought experiment, and that very few of those presentations bothered to acknowledge that the experiment had, in fact, been done. The editor also noted plainly that Jansen himself had received few professional rewards for the work. Think about what that means. A man teaches himself to build instruments that do not exist. He cuts slits 250 times finer than a hair. He proves, with his own hands, in a basement, the reality of the strangest and most important effect in modern physics. And the field looks at what he has done, and it shrugs, and it moves on, and it goes back to calling the experiment a thought experiment as if his years of work had never happened. The next time someone tells you that science always recognizes its own, that good work always rises, remember Claus Jönsson, and remember how long the world left his stripes sitting in the dark. But here is what Jansen's experiment could not yet answer, and it is the question that turns this whole story stranger. Jansen fired beams of electrons, many electrons, all at once, streaming through the apparatus together. And so, a reasonable person could still object. A reasonable person could say, well, Of course you get an interference pattern. You have a whole crowd of electrons in there at the same time. They're bouncing off each other, jostling, interacting. The pattern is just the result of all that traffic. It does not tell us anything truly strange. To kill that objection, you would need to do something that sounds almost impossible. You would need to fire the electrons one at a time, one single electron completely alone in the apparatus, with no other electron anywhere near it. And then another, and then another. And you would need to wait and watch and see what a crowd of solitary, isolated particles, none of which ever met any of the others, chose to build. Part 4. Tonomira's 70,000 dots. The definitive answer came from Japan in 1989 from a physicist named Akira Tonomura and his colleagues at the Hitachi Advanced Research Laboratory. And the experiment they ran is, to my mind, one of the most quietly haunting things ever done in a laboratory. They built an apparatus around a field emission electron gun, a device capable of producing electrons with extraordinary coherence and control. The electrons passed through an electron biprism, the same kind of instrument Müllenstedt had pioneered, which served as the double slit. And then they did the crucial thing. They turned the intensity of the electron source down, down, and down, until the apparatus was firing fewer than 1,000 electrons every second. That sounds like a lot. It is not. At that rate, the physics of the setup guaranteed something remarkable. At any given instant, there was only one electron inside the entire apparatus. One. A single electron would be fired, would travel through the biprism, would land on the detector and be recorded, and only then would the next electron be released. There was, as close to literally as physics allows, zero chance of two electrons ever being inside the machine together. No traffic, no jostling, no crowd. Every electron made its journey utterly alone. And then they simply let it run, and they photographed the detector at 4 stages. And those 4 photographs are what I want to describe to you, because the textbooks reproduce them, but they rarely let you sit with them. In the first photograph, after about 100 electrons have been fired, you see almost nothing. Scattered dots sprinkled across the detector, with no discernible order to them at all. It looks like static. It looks like random noise. If this were all you had, you would conclude there was nothing here. No pattern, no structure, just particles landing where particles land. In the second photograph, after about 3,000 electrons, something has begun to happen, though you would not be certain of it yet. There are faint hints of structure in the noise, a suggestion of vertical density here, a thinning there. It is like watching a face begin to resolve out of the grain of an old photograph before you are sure it is really a face. In the third photograph, after about 20,000 electrons, there is no longer any doubt. The bands are there, clear vertical stripes of density, separated by clear stripes of emptiness, an interference pattern emerging out of what only moments ago in the first photograph looked like pure chaos. And in the fourth photograph, after about 70,000 electrons, the pattern is complete, fully formed, unmistakable. Bright bands and dark bands marching across the detector, an interference pattern as crisp and as regular as anything Thomas Young saw on his wall in London, an interference pattern that can only mean waves. Now I need you to hold both halves of this in your mind at once, because the whole strangeness lives in the gap between them. Every single one of those 70,000 electrons arrived at the detector as a dot, a single, sharp, localized point of impact, not a smear, not a wave washing across the surface, a dot. Each electron, individually, was unambiguously a particle, a single, indivisible thing that struck one specific place. There was nothing wave-like about any individual electron, and yet the 70,000 dots taken together, each one made by a particle that travelled completely alone, with nothing to interfere with, assembled themselves into the interference pattern of a wave. Sit with the contradiction, because Richard Feynman, who understood quantum mechanics about as well as anyone who has ever lived, sat with it, and he called the double-slit experiment the one true mystery of quantum physics. Not one of the mysteries, the mystery. He argued that every other strange thing in the quantum world, entanglement, superposition, the lot of it, all of it traces back in the end to what happens when a single particle meets 2 open slits. And what happens is this: a single electron, fired alone, with no other electron anywhere near it, somehow knows about both slits. It somehow explores both paths, and when it lands, as a single dot, it lands in a position that only makes sense if it had, in some manner we do not have good words for, gone through both slits at once and interfered with itself on the way out. That is the first layer. That is the famous part. And the first layer has one more move in it, the move you've heard before. Because in Tonomira's experiment, as in every version of this experiment, if you place a detector at the slits, a device that records which slit each electron actually passes through, the interference pattern dies. Immediately. Completely. The stripes vanish, and the electrons begin landing in two simple clusters, behaving like the ordinary little projectiles your intuition always wanted them to be. The mere act of recording which path the electron took destroys the wave. Observation, whatever observation turns out to mean, changes the outcome. That is the version you know, and for most people, that is where the story stops. The spooky version. The version where you look, and the universe somehow notices and the pattern changes. It is genuinely strange, and it is genuinely true, and it is also, I am sorry to tell you, the shallow end. Because by the 1970s, a much harder question was already burning quietly in the background. A question the popular accounts of this experiment almost never ask out loud. Not what happens when you observe. We know what happens when you observe. The harder question is why. Why does observation change the outcome? What is it physically about the act of measurement that reaches into this delicate thing and destroys it? And the answer that physics had been giving for half a century, the comfortable, mechanical, common-sense answer, was about to be shown to be wrong. Before we leave Tonomira's experiment, I want to linger on those 4 photographs a little longer, because I think they are worth more attention than they usually get, and because they contain, in a single sequence of images, the whole strangeness of the quantum world made visible to the human eye. Imagine you're in the room when the experiment runs. The apparatus hums quietly. The electron source is turned down so low that the machine is firing barely a few hundred particles every second, each one alone, each one making its small solitary journey, and then waiting, politely, for its turn to be recorded before the next is released. And you are watching the detector, and at first there is almost nothing to watch. A dot appears, then somewhere else entirely another dot, then another, with no relationship to the first two that you can see. If you had to bet, in those first minutes, on what was being built, you would bet on nothing. You would bet on noise. You would say, these are particles, they are landing where particles land, there is no order here and there is not going to be any. And you would be wrong, and the wrongness would creep up on you slowly, which is the unsettling part. Because if you had the patience to stand there for the hours it takes, you would watch order arrive without ever being able to point to the moment it arrived. No single dot makes the pattern. No single electron is responsible. Each one lands as a particle, in a single place, by itself. And yet the bands assemble anyway, band by band out of tens of thousands of individual unrelated solitary impacts, as if every one of those electrons, fired alone, knew something about a pattern it was helping to build but could never itself see. Each electron is a single note. None of them ever hears the music, and the music plays anyway. That is the thing Feynman wanted his students to feel, and the thing the textbooks tend to flatten into a diagram. A single electron with no companions, with nothing to interfere with, fired across an apparatus in which it is utterly alone, still somehow comes through carrying the influence of both slits, still lands in a place that only makes sense if it had been a wave passing through 2 openings at once. The pattern is not in any electron. The pattern is in all of them, and that gap between the single particle and the collective wave is the gap that everything else tonight lives inside. Part 5. The crack. It was never the bump. The comfortable answer went like this. A detector is a physical object. When you place a detector at the slits to find out which one an electron went through, that detector has to physically interact with the electron in order to detect it. And any physical interaction has consequences. The detector, in the act of measuring, gives the electron a tiny kick. It transfers a little bit of momentum. It nudges the electron off course, just slightly, just enough. And that nudge, multiplied across thousands of electrons, randomizes their trajectories enough to smear the delicate interference fringes into nothing. The detector bumps the particle. The bump destroys the pattern. This explanation has a great deal going for it. It is intuitive. It is mechanical. It makes the kind of sense your body understands, the sense of one solid thing striking another. and it leans on something real, the Heisenberg uncertainty principle, which genuinely does tell us that you cannot pin down a particle's position without disturbing its momentum. For roughly half a century, from the founding of quantum mechanics through to the 1980s, this was the answer. The detector disturbs the particle. Ask a physicist why measurement kills interference, and the disturbance, the bump, is what you would hear. And in 1982, two physicists took that answer apart. Their names were Marlon Scully and Kai Druhl, and they published a paper in a journal called Physical Review A. It was a theoretical paper, a paper of pure reasoning, and what it proved was this. You can design a version of this experiment in which you obtain complete information about which slit the particle went through, and yet the disturbance you impart to that particle, the physical kick, is far too small to account for the loss of the interference pattern. You can know the path. The pattern still dies, but the bump is nowhere near big enough to have killed it. So if it was not the bump, what was it? The answer Scully and Druhl gave is the hinge of this entire story, so let me say it slowly. The interference does not vanish because the particle was kicked. It vanishes because the particle became entangled with the detector. Information about the particle's path became encoded, stored, written into the quantum state of another system, and it is the existence of that information, its availability, not any physical disturbance, that destroys the wave. If that sounds abstract, let me give you the experimental proof, because this did not stay theoretical for long. In 1998, a team at the Max Planck Institute in Germany, the physicists Dürr, Non and Rempe, ran exactly this kind of experiment using rubidium atoms in an atom interferometer. They marked the path of the atoms in a way that recorded which way each atom went. The interference vanished just as expected, and then they measured carefully the size of the physical disturbance their path marking had caused. And they reported in the journal Nature in plain language that the back action, the mechanical kick, was far too small to explain the disappearance of the interference pattern. The pattern had died. The bump had not killed it. The thing that killed it was the correlation, the entanglement, the fact that the information about the path now existed, written into another system. And here is the detail that should stop you. It did not matter at all whether any human being ever read that information. Nobody had to look at it. Nobody had to know it. The mere fact that the information existed somewhere in physical form was enough to destroy the wave. A few years earlier, in 1996, a physicist named Berthold Georg Englert had taken this insight and sharpened it into a precise mathematical statement, published in Physical Review Letters. He defined two quantities. The first he called distinguishability, written as the letter D. Distinguishability measures how much information is available about which slit the particle went through, on a scale from 0 to 1. 0 means no path information exists anywhere. 1 means the path is fully knowable. The second quantity he called visibility, written as the letter V. Visibility measures how clear and sharp the interference pattern is, also on a scale from 0 to 1. 0 means no fringes at all. 1 means perfect, crisp interference. And Englert proved that these two quantities are bound together by a strict relationship. D squared plus V squared is always less than or equal to 1. They trade off against each other. As distinguishability goes up, visibility must come down. As path information becomes available, interference must fade. And the reason that relationship holds is not mechanical. There is no bump in that equation. There is no kick. The trade-off is informational. It is about what is knowable, not about what was disturbed. I want to be honest with you about why this matters so much, because at first glance it can sound like a technicality, a fine distinction physicists fuss over. It is not a technicality. It is the crack in the wall through which the entire second layer of this experiment pours. Because as long as you believed the explanation was mechanical, as long as you believed it was a physical kick destroying the pattern, the experiment stayed comfortable. A detector is a thing. It bumps the particle. We understand bumps. But the moment you accept that it is information, and not disturbance, that governs whether the wave survives, you have opened a door, and on the other side of that door is a set of questions that physics has now spent more than 40 years trying and failing to answer. What exactly counts as information? Information available to whom? Does it matter if anyone ever reads it? Does it matter if the information is recorded by a conscious mind, or by a machine, or by a stray molecule of air drifting through the apparatus? Does it matter when the information is recorded, before the particle is detected, or during, or even after? These are not philosophers' questions. Every one of them turned out to be an experimental question. Physicists built machines to ask them, and the answers those machines returned are what the rest of tonight is about. But before we walk through that door, I want to give you the phrase that I think sits at the very bottom of this. Hold on to it the way you are holding on to the others. A record does not need anyone to read it. That is the quiet, strange truth that Scully and Drool cracked open in 1982. The universe responds to the existence of a record, and a record, it turns out, does not need a reader. To understand where that idea leads, we need to spend some time with one of the most extraordinary minds in the history of physics, because the experiment that pried this door fully open was not dreamed up by a rebel, or an outsider, or a crank on the fringes. It was dreamed up by a man at the absolute centre of 20th century physics, a man who had worked alongside Niels Bohr, who had named the black hole and the wormhole, who had helped build the atomic bomb, and who, at the age of 67, asked a question so unsettling that the physics community spent 2 full decades pretending it was merely philosophical, before anyone found the nerve to test it. I want to make sure the size of this shift is clear, because it is easy to nod along and miss it. For half a century, the picture in every physicist's head was mechanical, and mechanical pictures are comfortable because our bodies understand them. A detector is a thing. It touches the particle. The touch jostles the particle. The jostle ruins the pattern. Cause and effect, contact and consequence, the physics of one solid object meeting another. You can almost feel it in your hands. And as long as that picture held, the double-slit experiment, strange as it was, stayed inside the realm of things that behave. The wave dies because something hit it. Fine, unsettling, but fine. Scully and Drool, and then the rubidium atom experiment that confirmed them, removed the hand from the picture. They showed there is no jostle large enough to be the culprit. The wave still dies, and nothing hit it hard enough to kill it. What kills it is that somewhere, the answer to the question which slit now exists. The information has been laid down, and once you accept that, you have left the comfortable mechanical world behind for good, because information is not a thing you can hold. It does not have a weight. It does not deliver a blow. And so the question of what governs the deepest behaviour of reality has quietly stopped being a question about forces and collisions and become a question about records and knowledge and what counts as a fact. That is not a small adjustment to the old picture. It is a different picture, and almost nobody outside the journals was told the picture had changed. Part 6. Wheeler and the Question of the Past. John Archibald. Wheeler was born on the 9th of July 1911 in Jacksonville, Florida. His parents were both librarians, which is a small detail, but I find it a quietly fitting one for a man who would spend the end of his life arguing that the universe is made of information. He was a prodigy of a calmer kind than Thomas Young. He entered Johns Hopkins University at 16, earned his doctorate at 21, and won a fellowship that sent him to Copenhagen to study under Niels Bohr, the Danish physicist who, more than any other single person, had built the strange new science of quantum mechanics. Wheeler's fellowship application contained one sentence that tells you almost everything about the kind of physicist he was. He wrote that he wanted to work with Bohr because Bohr, in his words, sees further than any man alive. In January of 1939, Bohr arrived at Princeton University carrying news that would reshape the entire century. German chemists had succeeded in splitting the uranium atom. Nuclear fission was real. Bohr and Wheeler immediately began working together on the theory of how fission actually worked, and on the 1st of September, 1939, the very day Germany invaded Poland and the Second World War began, they published their paper on the mechanism of nuclear fission in the journal Physical Review. Wheeler was 28 years old. He spent the war years on weapons work. He moved to the Hanford site in Washington state, where enormous reactors were producing plutonium for the bomb, and when one of those reactors mysteriously shut itself down shortly after starting up, it was Wheeler who diagnosed the cause, a particular atom, xenon-135, produced inside the reactor and poisoning the chain reaction. His solution kept the plutonium program on schedule, and here is where I have to tell you the part of Wheeler's story that the physics textbooks almost always leave out, because without it, you cannot understand what he did next. John Wheeler had a younger brother. His name was Joe, and while John Wheeler was at Hanford, helping to build a weapon, His brother Joe was a soldier, fighting in the Italian campaign. Joe knew, in the vague and unspecified way that the families of classified workers sometimes know, that his older brother was involved in something enormous and secret, and at some point Joe sent his brother a postcard from the front. The message on it was 2 words long: "Hurry up." Joe Wheeler was killed in Italy in October of 1944. He left behind a young widow and an infant daughter, and the bomb that his brother was helping to build was not ready. It would not be finished, would not be used, until August of 1945, 10 months after Joe died. John Wheeler did the arithmetic of those 10 months for the rest of his life. He wrote many years later that he could not stop thinking, and had never stopped thinking, that the war might have been over in October of 1944, that his brother might have lived if the work had only gone faster. When, decades afterward, in 1968, the President of the United States presented Wheeler with one of the highest honors in American science, Wheeler's response was just 3 words long. He said, "I felt forgiven. I'm not telling you this because it is touching background. I'm telling you this because it connects directly to the physics. Because the man who spent decades of his life haunted by a question about the past, by the unbearable question of whether a different decision, a faster decision, could have produced a different history, whether his brother's death sat at the end of a timeline that might have run another way, that man became the physicist who asked whether the past is fixed at all, whether a choice made now could reach backward and help determine what had already happened. There is no way to know how much of one fed the other, but I do not think it is an accident that this particular question found this particular man. In 1978, at a scientific symposium held in honor of Richard Feynman, Wheeler presented a thought experiment. It is called the delayed choice experiment, and it works like this. You fire a single photon, a single particle of light, at a half-silvered mirror, a device physicists call a beam splitter. A beam splitter does exactly what it sounds like. It gives the photon a 50-50 chance. The photon may pass straight through, taking one route, call it path A. Or it may be reflected, taking another route, path B. Further mirrors then redirect both possible paths so that they travel toward a single crossing point. And at that crossing point, the experimenter has a choice to make. The experimenter can place 2 detectors there, one watching each path. If you do that, each photon is caught on one path or the other, and you learn which route it took. It behaves like a particle, a thing that picked a road and travelled it. Or the experimenter can instead place a second beam splitter at the crossing point, recombining the 2 paths into one. And if you do that, the 2 paths interfere with each other, and the photon behaves as though it had travelled both routes at once. It behaves like a wave. So far, this is just the double-slit story dressed in different equipment. Here is Wheeler's actual question, the one that earned the symposium its uneasy silence. What if you wait? What if you let the photon enter the apparatus, let it pass the first beam splitter, let it commit, so to speak, to being a particle on one path or a wave on both, and only then, only after the photon is already inside and on its way, you make your choice about which configuration to use. Quantum mechanics gives a clear and disturbing prediction. It says the timing does not matter. If you insert the second beam splitter, even at the last possible instant you get interference. The photon will have behaved as a wave. If you leave it out, you get witch path detection. The photon will have behaved as a particle. The photon's behaviour all the way back through the apparatus conforms to a choice you had not yet made when the photon entered. Wheeler was careful, and I want to be careful with you, about what this does and does not mean. He did not think a signal was being sent backward in time. He did not think you could use this to send a message to the past. What he thought was stranger and more fundamental than time travel. He thought the lesson was that it is simply wrong to say the photon had a definite history, a definite path, before the measurement defined one. The past of the photon was not a fact sitting in storage, waiting to be discovered. The past was something the act of measurement helped to write, and then Wheeler did the thing that made the idea genuinely vast. He took it cosmic. He pointed out that you do not need a laboratory beam splitter to run this experiment. The universe has already built one for you. There are quasars, brilliant objects in the deep distance, whose light, on its way to Earth, passes a massive galaxy. And the gravity of that galaxy bends the light around both sides of it, splitting a single beam into 2 paths that travel for billions of years before arriving here. an astronomer on Earth today, choosing how to point an instrument, choosing whether to look for which path information or to recombine the beams and look for interference, would be making a delayed choice about a photon that committed to its journey billions of years ago. Long before the Earth existed, long before the Sun existed, long before there was any life anywhere to observe anything at all. Wheeler put it in a sentence that gets quoted in every documentary, though its full weight is rarely unpacked. He said that we are participators in bringing into being not only the near and the here, but the far away and the long ago. Read that again. He is not saying we discover the distant past. He is saying we take part in bringing it into being. That is an extraordinary claim, and for 2 decades the physics community treated it as a philosophical curiosity, a clever puzzle, the kind of thing you discuss after dinner and then set aside. Because surely you could never actually test it. Surely the delayed choice was, like the electron double slit before it, destined to live forever as a thought experiment. But here is the thing about thought experiments in this particular field. They have a way of refusing to stay imaginary. And the experiment that finally tested Wheeler's delayed choice, the experiment that dragged it out of the realm of philosophy and onto a laboratory bench, also turned out to be the single most misunderstood experiment in the history of physics. I want to stay with John Wheeler for a moment longer, because there is more to the shape of his life than the delayed choice experiment, and the rest of it deepens what that experiment was really asking. Think again about the postcard. 2 words. Hurry up. A young man at the front in Italy, writing to his older brother, knowing only that his brother was somewhere in America doing something that might end the war, and asking him, in the only way the censors would allow, to do it faster. And then think about the 10 months. The bomb finished in August of 1945. Joe killed the previous October. John Wheeler, a man of immense precision, a man who had diagnosed a poisoned reactor by tracking a single isotope, would have known those 10 months down to the day. He would have known that the gap between the timeline that happened and a timeline that might have been was not abstract. It had a length, it had a number, and his brother was inside that number. A man does not carry an arithmetic like that for 60 years without it shaping the questions he finds himself unable to stop asking. And the question Wheeler could not stop asking in the end, dressed in the language of photons and beam splitters, was a question about whether the past is a finished thing, whether what has happened is sealed, fixed, beyond all reach, or whether, in some strange and limited and non-magical way, the past stays open, stays unfinished, until the present asks the question that closes it. He did not believe his delayed choice experiment would let anyone send a message backward, or undo a death, or rewrite a history. He was far too careful a physicist for that. But he did come to believe, on the strength of the experiments, that the past of a single photon is not a fact lying in storage. It is a story that the act of measurement helps to write, and it is hard, knowing what he carried, not to hear the private question underneath the public one. There is one more piece of Wheeler's life worth knowing here, because it shows you the kind of physicist he was. Wheeler also supervised at Princeton a doctoral student named Hugh Everett, the young man who, in 1957, proposed the many worlds interpretation. Everett's idea that the universe branches at every measurement and all outcomes are real was so radical that the physics establishment of the time effectively crushed it. Everett left academic physics, went to work for the defense industry, and never published another physics paper. He died relatively young, and Wheeler had a complicated relationship with the idea ever after, championing it at first and then stepping back from it. But notice the pattern, because it is the same one we saw with Young and with Jansen. A genuinely strange and genuinely serious idea is put forward, and the establishment, made uncomfortable, pushes it away, and the person who carried it pays a price. Wheeler stood close to that pattern more than once, and then, with the delayed choice experiment, he handed the field one more idea it was not ready to absorb. He seems, by the end, to have made his peace with that. He once said that he expected someday that we would all grasp the central idea of how the universe works and find it so simple, so beautiful, so compelling that we would say to one another, "Oh, how could it have been otherwise? How could we have been so blind for so long?" Part 7. The Eraser and the Lie About It. The experiment is called the Delayed Choice Quantum Eraser, and you have almost certainly encountered some version of it before, because it has been explained on the internet more times than anyone could count, and nearly every one of those explanations is wrong. Not slightly wrong. Wrong in a specific direction, a direction that makes the result sound more magical and more comfortable than it actually is. So I am going to walk you through the real experiment, the actual apparatus, slowly, because the details are where the truth lives, and the truth is stranger than the myth. The landmark version of this experiment was carried out by a team including Yoon-ho Kim and once again Marlon Scully, the same physicist who had proposed the idea 16 years earlier. It was published in Physical Review Letters in January of the year 2000, and the work was done at the University of Maryland in Baltimore County. Here is what they built. A laser fires a beam of light through a double slit. Behind that double slit sits a special crystal, made of a material called beta-barium borate, which physicists shorten to BBO. This crystal does something genuinely useful. When a single photon from the laser strikes it, the crystal can split that one photon into two new photons, each carrying half the energy of the original. These two new photons are born together, from the same parent, and they are entangled. Their quantum states are linked. Physicists call one of them the signal photon and the other the idler photon. Now, because the laser passed through a double slit before reaching the crystal, there are two regions in the crystal where this splitting can happen. Call them region A and region B, lined up with the two slits. If the splitting happens at region A, the photon pair effectively came from slit A. If it happens at region B, the pair came from slit B. After the crystal, the two photons of each pair are sent in different directions. The signal photon goes one way, through a lens toward a detector the physicists labelled D0. This detector D0 can slide back and forth, scanning across its position, recording exactly where each signal photon lands. D0 is the screen. It is the place where an interference pattern would show up, if there is one. The idler photon, the signal photon's entangled twin, goes the other way, into a separate and more elaborate set of optics, and the idler's path runs it into a series of beam splitters. Depending on the outcomes at those beam splitters, the idler photon ends up at one of four detectors, labelled D1, D2, D3 and D4. And the geometry is arranged with great care so that two of those detectors, D3 and D4, can only receive an idler whose path is identifiable. If the idler lands at D3, you know its pair came from slit A. If it lands at D4, you know it came from slit B. Those two detectors preserve the witch path information, but the other two detectors, D1 and D2, sit behind a final beam splitter that recombines the idler's possible routes so thoroughly that by the time the idler arrives, there is no longer any way to tell which slit it came from. Those two detectors erase the witch path information, and now the single most important detail of the entire apparatus. The path that the signal photon travels from the crystal to detector D0 is about 2.5 meters shorter than the path the idler photon travels to reach its detectors. Light covers 2.5 meters in a very short but very real amount of time. The consequence is this. The signal photon arrives at D0 and is recorded, its landing point written down, about 8 nanoseconds before its idler twin reaches the beam splitter that will determine whether the path information is preserved or erased. Let me put you inside that. Slow it down. A pair of photons is born in the crystal, they separate. The signal photon races toward D0. It strikes the detector. Its dot is on the screen. Its position is now recorded, fixed, written into the data. The experiment, for that photon, is over. And only now, 8 nanoseconds later, an eternity by the standards of light, does the idler photon, still in flight, still travelling, finally reach the apparatus that has not yet done anything to decide whether its path will be remembered or forgotten. The record of where the signal photon went exists before the choice about its twin has been made. Hold that image. We're going to need it. Now the results, and here is where you must pay close attention, because what the experiment found is not what most people think it found. If you look at detector D0 on its own, all the signal photons it recorded without sorting them by anything else, you see no interference pattern. None. No fringes. Just a smooth, featureless blob, a single broad hump of photons. This is crucial. If you were standing in that laboratory, watching the signal detector in real time, you would never, under any circumstances, see a pattern. Whatever is done to the idler photons far away in their separate optics, the raw picture at D0 is always the same smooth blob. But then the researchers did something with the data. They sorted it. For each signal photon recorded at D0, they checked which of the 4 idler detectors had caught its entangled twin, a technique called coincidence counting. And when they sorted the D0 detections this way, the smooth blob came apart into 4 separate subpatterns. The signal photons whose idler twins had landed at D1, where the path information was erased, formed a clear interference pattern. Bright bands and dark bands. The signal photons whose idlers landed at D2, also erased, formed an interference pattern as well, but shifted, offset by half a step, so its bright bands sat exactly where the D1 pattern's dark bands were. And the signal photons whose idlers landed at D3 or D4, where the path information was preserved, formed no interference at all, just smooth humps. And here is the mathematical punchline, the part the magical explanations skip. Those 2 interference patterns, the D1 pattern and the shifted D2 pattern, are perfect complements of each other. If you add them back together, every bright band of one falls on a dark band of the other, and they cancel exactly into a smooth hump. Add that to the 2 humps from D3 and D4, and you recover the original featureless blob at D0. The interference was always there. It was always inside the data. It was simply hidden, perfectly cancelled by its own mirror image, and the only way to make it visible was to sort the data using information that did not arrive until after the signal photon had already been recorded. This is the result that launched 1,000 misleading videos, because at first glance it looks like the future is reaching back to rewrite the past. The idler is detected after the signal. The idler's fate, erased or preserved, seems to decide whether the signal photon's behavior was wave-like or particle-like 8 nanoseconds earlier. So the story goes, the future changed the past. The signal photon retroactively went through both slits, or one, depending on what happened to its twin. That story is wrong. And understanding exactly why it is wrong is the key that unlocks the second layer, so stay with me. The signal photon and the idler photon were entangled from the instant they were born in the crystal. An entanglement, all by itself, destroys single particle interference. This is the piece the magical version always omits. Because the signal photon is entangled with the idler, the signal photon, considered on its own, is not in a clean, pure quantum state. It is in what physicists call a mixed state, and a particle in a mixed state simply does not show an interference pattern. There were never any fringes at D0 to resurrect. The interference was dead the moment the photon pair was created. As the physicist Sean Carroll put it bluntly, entanglement of any sort kills interference. So what do the erasure detectors actually do? They do not reach back in time and bring a dead pattern to life. What they do is sort. They take the signal photon data, which was always a featureless blob, and they divide it into subgroups based on what happened to each photon's twin. And in the subgroups where the idler's path information was erased, the underlying mathematics of the entangled pair allows an interference pattern to be visible within that subgroup. In the subgroups where the path information was preserved, it does not. The interference was hidden in the correlations all along. Sorting reveals it. Sorting does not create it. And the reason you can never use this to send a message backward through time is beautifully simple. The signal photons in every subgroup land at D0 in the same place, at the same time, with the same overall smooth distribution. Standing in the lab, you cannot tell, even in principle, which subgroup any individual photon belongs to. To do the sorting, you need the idler data, and the idler data travels to you at the speed of light and not one bit faster. The pattern only appears once the ordinary slower-than-light information about the idler detections has been carried over and matched up with the signal data. The analyst Ruth Kastner has written that the experiment neither erases nor delays anything in the way the popular version claims. The physicist Sabine Hossenfelder has emphasized correctly that nobody watching D0 in real time can ever distinguish anything but the blob. The eraser does not rewrite history. It sorts a record. Now, most careful explanations stop right here. They debunk the time travel story, they explain entanglement and sorting, and they move on, satisfied. But this is exactly the point where I want to go further, because debunking the magical version is not the end of the mystery. It is the beginning of a deeper one. Because think about what we have just established. The comfortable misreading said the future reaches back, and that consciousness somehow is involved in the reaching. And as wrong as that misreading is, notice what it quietly preserves. It keeps us important. It keeps human awareness special, central, the thing the universe is responding to. The real result takes that away. The real result says the wave died not because anyone looked, but because information existed, encoded in the state of another particle, and whether that information was ever read by a mind, by a machine, by anything at all, made no difference whatsoever. The variable was never observation. The variable was the existence of a record, and a record, as I told you a few minutes ago, does not need anyone to read it. Which raises the obvious next question. If the variable is just the existence of information and not a conscious observer, then how far can you push that? What if the choice to record the information, or not, were made by a machine? What if it were made under conditions where no signal of any kind, at any speed, could connect the choice to the experiment? Would the universe still comply? And in the years after the Kim experiment, physicists built the machines to find out. Part 8. Vienna, and the machines take over. The first thing physicists did was take the human being out of the moment of choice. In 2007, a team including the physicist Alain Aspect, one of the most important experimentalists alive, published a result in the journal Science. They had finally realized Wheeler's delayed choice experiment properly with single photons. Their photons came from individual nitrogen vacancy color centers in tiny diamond crystals, which are about as close to a genuine, controllable, one-at-a-time single-photon source as nature allows. They built an interferometer 48 meters long, which is important because 48 meters gave them room. It guaranteed that the photon was already deep inside the apparatus, had already passed the first beam splitter, before the choice of configuration was made, and the choice was not made by a person. It was made by a quantum random number generator, a device that sampled random electronic noise and spat out an unpredictable bit, wave or particle, with no human being anywhere in the loop. The results were exactly what quantum mechanics predicted. When the machine chose the wave configuration, the photon showed about 94% interference visibility, a beautiful clean pattern. When the machine chose the particle configuration, the experiment determined the photon's path with an error rate below 1%. And crucially, it made absolutely no difference that the choice came after the photon had entered. The delayed choice and an ordinary preset choice gave identical results. Wheeler's 1978 thought experiment, the one the community had spent 2 decades treating as philosophy, was now a confirmed laboratory fact. And the entity making the choice that the photon's history conformed to was a machine sampling noise. That honestly should have been the end of the consciousness story right there in 2007. A random number generator decided whether a photon behaved as a wave or a particle, and the photon obeyed. No mind required. But the story did not end, because the physicists in Vienna were not finished pulling the legs off the table. In 2012, the group led by Anton Zeilinger, working at the Institute for Quantum Optics and Quantum Information in Vienna, published a paper in Nature Physics with a title that sounds like a paradox folded in half: Experimental Delayed Choice Entanglement Swapping. And what they did was genuinely difficult to hold in your head, so let me build it carefully. They used 2 completely separate sources of photons. The first source produced a pair of entangled photons, call them photon 1 and photon 2. The second, independent source produced its own entangled pair, photon 3 and photon 4. Now 2 people, by convention always called Alice and Bob, each took 1 photon from the outer edges of this arrangement. Alice measured photon 1. Bob measured photon 4. They did this quickly, about 35 nanoseconds after the photons were created, and they recorded their results. Permanently, the measurements were done, the data was written, the ink, so to speak, was dry. Meanwhile, the 2 inner photons, photon 2 and photon 3, were sent on a much longer journey through more than 100 meters of optical fiber to a third location, operated by a character the paper calls Victor. And because of that longer path, photons 2 and 3 did not arrive at Victor's apparatus until about 520 nanoseconds after they were born. That is nearly half a microsecond after Alice and Bob had already measured their photons and locked in their results. And then Victor's apparatus did one of 2 things, and which one it did was decided by a quantum random number generator, a machine. If the machine chose the first option, Victor's apparatus performed a particular joint measurement on photons 2 and 3 that, through the mathematics of entanglement swapping, reached out and retroactively entangled photons 1 and 4. Photons 1 and 4, remember, had never met. They came from different sources. They had already been measured by Alice and Bob. And yet, after Victor's measurement, when the researchers examined Alice and Bob's recorded data, photons 1 and 4 showed the unmistakable signature of entanglement. They violated a Bell inequality. They were correlated in a way that classical physics flatly cannot produce. If the machine chose the second option instead, photons 1 and 4 showed only ordinary classical correlations, no entanglement. Let me state plainly what that means, because it deserves to land. Alice and Bob measured their photons and wrote down the results. Then, half a microsecond later, a machine sampling quantum noise flipped a bit. And depending on which way that bit fell, the already recorded data described either a pair of entangled photons or a pair of ordinary ones. The authors of the paper wrote, with admirable honesty, that if you insisted on viewing the quantum state as a real physical object, you would be forced into the paradoxical conclusion that future actions appear to influence past, already irrevocably recorded events. And no human consciousness was anywhere in the decision chain. A machine chose. The recorded past reorganized itself to match. The following year, 2013, the same group went further still. They published a paper, this time in the Proceedings of the National Academy of Sciences, on quantum erasure with a causally disconnected choice. The phrase causally disconnected is doing enormous work in that title, so let me unpack it. This time, the choice of whether to erase or preserve the path information was made under what physicists call Einstein locality conditions. The choice event and the photon's passage through the interferometer were separated by enough distance and arranged in enough of a hurry that not even light, not even a signal travelling at the absolute maximum speed the universe permits, could have carried news of the choice to the experiment in time to influence it. Under the rules of relativity, there was no possible causal connection between the choice and the measurement. None in any reference frame. They ran it two ways. Once over a 55-metre fibre link inside a Vienna laboratory, and once, spectacularly, over a 144-kilometre free space link, beaming photons between two islands in the Canary Islands, from La Palma to Tenerife. A quantum random number generator made every choice, and the results, once again, matched the predictions of quantum mechanics exactly. When the machine erased the path information, interference appeared in the sorted data. When it preserved the path information, no interference appeared. Under conditions where the laws of physics themselves forbid any causal link between the choice and the experiment, the universe still produced a result perfectly consistent with that choice. The paper concluded that no naive realistic picture is compatible with their results. And then, in 2018, came the most direct test of all. Not of timing this time, but of the human mind itself. It was called the Big Bell test, and it was published in the journal Nature, and it did not involve one laboratory. It involved the entire planet. On the 30th of November, 2016, more than 100,000 people all around the world sat down at their phones and computers and played an online video game. The game was designed to do one thing: to extract from each player a stream of genuinely unpredictable, hard-to-guess choices. Over the course of that day, those 100,000 people generated more than 97 million random bits. And those bits were not just collected, they were streamed in real time to 13 separate quantum physics experiments running in 12 laboratories on 5 continents. The human choices replaced the machines. Where those experiments would normally have used a quantum random number generator to decide their measurement settings, on that day they used the unpredictable decisions of 100,000 human beings instead. The Big Bell test confirmed the violation of local realism across all 13 experiments. But the finding I want you to hold on to came out of the experiment running in Munich at the Max Planck Institute of Quantum Optics. That experiment did something very deliberate. It directly compared the results when the measurement settings were chosen by human beings against the results when the very same settings were chosen by a quantum random number generator. A side-by-side test, humans versus machine, and the two sets of results were statistically indistinguishable. Not similar, not close, indistinguishable. 100,000 human minds deliberating, choosing, and a machine sampling electronic noise produced the same violations to within the limits of measurement. I want to pause here because we have arrived somewhere, and I do not want us to walk past it too quickly. There is no experiment anywhere in the entire history of quantum mechanics that has ever found human consciousness to play a special role in any of this. Not one. Every experiment ever designed to test whether awareness matters, whether a mind makes a difference, has found the same answer. It does not. The universe, as far as our most careful measurements can tell, does not distinguish between you and a random number generator. It does not distinguish between a decision made by a thoughtful Nobel laureate and a decision made by a flicker of electronic static. It does not distinguish between an intention and a coin flip, and in 2019, a team at Heriot-Watt University in Edinburgh pushed even into the question of whether reality itself is the same for everyone. They built a 6-photon experiment based on a famous old thought experiment from the physicist Eugene Wigner, a scenario in which two different observers, both applying quantum mechanics correctly, end up holding genuinely contradictory accounts of what happened. Not different opinions about the same fact, but different facts. For decades, it was assumed this could never be tested. The Edinburgh team tested a version of it, and they found that a particular combination of 3 reasonable-sounding assumptions, that quantum mechanics applies to systems of any size, that different observers can reason consistently about each other, and that every measurement yields one single definite outcome, that those 3 assumptions cannot all be true at once. The relevant inequality was violated by 5 standard deviations. At least one of those 3 comfortable beliefs is wrong, and the experiment could not tell us which. So that is the experimental record. That is what the machines, built across 40 years on multiple continents, have actually shown us. And it has steadily, patiently removed us from the centre of the story. The consciousness version of the double-slit experiment was always the version that made us the protagonist. The real version, the second layer, has been quietly informing us, experiment by experiment, that we were never the protagonist. We were never the observer the universe was waiting for, which leaves us holding a question we can no longer avoid, and it is the question the rest of tonight belongs to. If observation changes the outcome, but observation is not consciousness, then what physically is observation? What does it actually mean for something to be observed? I want to slow down on the Big Bell test for a moment, because the more I think about that single day, the 30th of November 2016, the more remarkable it becomes. Picture it from above. 100,000 people scattered across every inhabited continent, in cities and small towns, in the morning and the evening and the middle of the night depending on where they sat, all of them tapping at screens, playing a small game whose only purpose was to be unpredictable. Most of them, almost certainly, did not fully understand what they were part of. They were not in laboratories. They were on couches, on trains, at kitchen tables, and the stream of unpredictable choices coming out of their fingers was being gathered up in real time and routed to 13 of the most sensitive physics experiments on Earth, where it was used that day to decide how entangled particles would be measured. 100,000 strangers, briefly, were the random element at the heart of frontier physics. And the reason the physicists wanted human beings for this is itself worth understanding, because it tells you how seriously they took the question. In a Bell test, the choice of measurement setting has to be genuinely free, genuinely unpredictable, genuinely uncorrelated with the particles being measured. If there was some hidden link, some subtle correlation between how the setting gets chosen and what the particles are going to do, it could fake the result. A machine, a random number generator, is itself a physical object, obeying physical law, and a sufficiently determined skeptic could always say, well, perhaps the machine's choices were secretly correlated with the particles all along. Human beings, with whatever it is that makes a human choice, were brought in as the hardest possible case. If anything in the universe could provide a choice that was truly disconnected from the particles, surely it was 100,000 independent human minds. And the answer came back, and the answer was that it made no difference. The Munich group's side-by-side comparison found human-chosen settings and machine-chosen settings producing violations that were statistically indistinguishable. The hardest case and the easiest case gave the same result. Whatever a human choice is, the universe did not treat it as anything special. It did not treat it as anything different from electronic noise. And notice once more, the long shadow of the pattern we have been tracing all night. Henry Brougham attacked Thomas Young rather than absorb the evidence that light is a wave. The field left Jansen's stripes in an untranslated journal for 13 years, rather than reckon with what one graduate student had built. The establishment pushed Hugh Everett's branching universes to the margins. Over and over, across 2 centuries, the same reflex. When the evidence is uncomfortable, it is so much easier to look away from the evidence than to update the belief. And the second layer of the double-slit experiment is, right now, sitting inside exactly that pattern. The papers are public, the Vienna results, the Big Bell test, the delayed choice confirmations, all peer-reviewed, all replicated, all freely available to anyone who wants to read them. Nothing is hidden. And yet the version of this experiment that the wider world still carries, the version in the popular books and the documentaries, is the comfortable first-layer version, the one where consciousness is the special ingredient, not because of a conspiracy, there is no conspiracy, but because the true version is harder to tell and harder to sell, and asks the listener to give something up. The evidence has been published. It is simply waiting, the way Jansen's stripes once waited, for the world to be ready to hear it. Part 9. So, what then is observation? Here is the strange position we are now in. We know, from a chain of experiments stretching across 2 centuries, that whether a particle behaves as a wave or a particle depends on whether information about its path exists. We know it is not consciousness. We know it is not the mechanical bump. We know a machine does just as well as a mind. But knowing what observation is not has only sharpened the question of what observation is. What physically, in concrete terms, is a measurement? What event exactly makes the wave die? The honest answer is that physics has 6 different answers to that question, and physicists have been arguing about those 6 answers, often bitterly, for nearly 100 years. I am going to walk you through all 6, but I want to be clear about why. I am not going to do it because the interpretation debate is the subject of tonight. It is not. The subject of tonight is the experiments and the people who ran them. I am walking you through the 6 interpretations because the experiments forced them into existence. The experiments asked a question so sharp that physics splintered into 6 camps trying to answer it. And those 6 camps, who agree on almost nothing, who hold conferences where the arguments turn into something close to shouting, who accuse one another of philosophical naivety, those 6 camps agree, every one of them, unanimously on a single point. And that point is the payoff of this entire video. So let us meet them. The first and most widely taught is the Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, the founders. And the first thing to understand about Copenhagen is that it is, in a sense, a refusal to answer rather than an answer. Bohr's position was that quantum mechanics does not describe what nature is. It describes only what we can say about nature. The wave function, in this view, is not a physical thing that lives out in the world and then collapses. It is a mathematical tool, a bookkeeping device for calculating the probabilities of what our instruments will show us. Asking what the electron is really doing between measurements, Bohr held, is not a hard question. It is not even a meaningful question. Copenhagen draws a line between the quantum world and the everyday classical world, and then it declines, firmly, to tell you where that line is or why it exists. Its critics have a sharp name for this. They call it shut up and calculate. The math works extraordinarily well. Copenhagen says, so do not ask what it means. The second interpretation is many worlds, proposed in 1957 by Hugh Everett, a doctoral student whose thesis supervisor was, as it happens, John Wheeler. Many worlds takes the boldest possible position. It says the wave function never collapses. Ever. Instead, every quantum measurement causes the universe to split, to branch, into separate versions, one for each possible outcome. In one branch, the electron went through slit A, in another branch it went through slit B, and both branches are equally physically real. The physicist Sean Carroll has argued that this is actually the simplest interpretation because it adds nothing to the mathematics. You just take the equation seriously and let it run. The cost, of course, is staggering. You must accept that reality is constantly fracturing into an unimaginable number of parallel branches, and that countless versions of you are being generated every instant. The third is the pilot wave interpretation, sometimes called de Broglie-Bohm, after Louis de Broglie, who first proposed it, and David Bohm, who revived it. Pilot wave says the particle is always a real, definite particle, with a definite position at every moment. It goes through one slit, not both. But alongside the particle there is also a real, physical wave, the pilot wave, and that wave does pass through both slits and interferes with itself, and the particle rides that wave like a surfer, steered along a definite path by the wave's shape. Everything is concrete, everything is determined. The apparent randomness in this view is just our ignorance of the particle's exact starting point. Pilot wave reproduces every experimental result perfectly, and yet, for reasons that have far more to do with history and personality than with physics, it spent decades pushed to the margins. The fourth is cubism, developed by Christopher Fuchs and Rüdiger Schack. Cubism says the wave function is not a physical thing at all. It is a tool that an agent uses to organize that agent's own expectations about its future experiences. A measurement is an action an agent takes, and the outcome is definite simply because the agent experienced it. And critically, in cubism, an agent does not have to be conscious in any mystical sense. The fifth is relational quantum mechanics, proposed by Carlo Rovelli, which says that quantum states are not properties that a system has on its own, but relationships between systems. An electron does not have a definite spin, full stop. It has a definite spin relative to a particular detector. There is no observer-independent quantum state, just as, in Einstein's relativity, there is no observer-independent velocity, and any physical system at all can serve as the observer. And the sixth, which most physicists now accept regardless of which of the others they prefer, is decoherence, which I am going to give its own beat in a moment, because it is the clearest physical picture we have. 6 interpretations. They disagree about almost everything that can be disagreed about. They disagree about whether the wave function is a real physical object or just a calculating tool. They disagree about whether particles have definite positions when nobody is measuring them. They disagree about whether the universe splits. They disagree about whether quantum probability is something objective out in the world or something subjective in the mind of an agent. They disagree about whether the question what is really happening is even a sensible thing to ask. The interpretive wars are among the most genuinely vicious in all of science, and they have been raging, unresolved, for the better part of a century. And yet, across every one of those battle lines, across all 6 camps, there is one statement that every single interpretation agrees on. Not one mainstream interpretation of quantum mechanics assigns any special role to human consciousness. Copenhagen says a measurement is a physical process involving large classical instruments. Manyworld says all outcomes simply happen, regardless of whether anyone is there. Pilot wave says particles follow definite paths steered by a physical wave, no mind involved. Cubism's agents need not be conscious. Relational quantum mechanics says an observation is a physical interaction between any 2 systems, and a rock counts as well as a person. Decoherence says the observer is the environment itself. I want you to feel the weight of that, because this is the emotional center of everything we have talked about tonight. The comforting version of the double-slit experiment, the one you were taught, the one that has sold a great many books, made human consciousness the special ingredient. It said the universe responds to awareness, to the mind, to you. It put us at the center of reality, and it felt quietly, almost spiritual. It told us that we mattered to the cosmos in some deep and structural way. And the real result, the second layer, the thing the experiments actually show, is that the universe never distinguished between you and a random number generator. Not in any experiment ever performed. Not in any interpretation any serious physicist holds. The choice made by a thoughtful human being and the choice made by electronic static produce, as far as reality is concerned, exactly the same thing. The universe was not waiting for you to look. It was never waiting for anyone to look. There is a loss in that. I will not pretend there is not. It is the loss of a certain kind of cosmic importance, the quiet reassurance that our awareness was somehow central to how things are. But I want to offer you the other side of it too, because I think there is one. There is a strange dignity in seeing this clearly, in being the kind of creature that can run the experiment, build the machine, read the result honestly, and accept what it says even when what it says is that we are not the protagonist. We may not be the observer the universe responds to, but we are, as far as we know, the only part of the universe that has worked out that it responds to anything at all. That is not nothing. That is in fact a rather extraordinary thing to be. So if it is not us, and it is not our minds, then who or what is doing the observing? What is the observer the universe actually answers to? The answer turns out to be everywhere. The answer turns out to be almost everything. And to see it, we need to talk about the most relentless, most thorough, most tireless observer in all of existence, the one that has been watching every particle in your body, without pause, since the moment you were born. And before we go looking for that observer, I want to name plainly what we have lost and what we have kept, because both halves are true and you should carry both. What we have lost is the idea that our looking is special. For a long time, the popular story led us believe that a conscious mind turning its attention toward a particle was the event that mattered, that human awareness sat at the hinge of reality. The experiments have taken that away, gently but completely. But notice what they have not taken. They have not taken the strangeness. They have not taken the wonder. The universe is still doing something extraordinary at the double slit. It is still true that a single particle, fired alone, comes through carrying the influence of both paths. It is still true that whether you get a wave or a particle depends on whether a record exists. None of that softened when consciousness left the picture. If anything, it grew. We simply learned that the strangeness was never about us. It was always about something deeper, something that was running long before there were minds to notice it, and will run long after, and that is worth knowing, even though it costs us our place at the centre. Part 10. The environment is already watching. In 1970, a German physicist named Heinz-Dieter Zeh published a paper that almost nobody read. It appeared in a journal considered at the time somewhat philosophical, somewhat off to the side of mainstream physics, and for roughly a decade it sat there, largely ignored. The physics community of 1970 was not interested in the measurement problem. They had Copenhagen. They had shut up and calculate. A paper that tried to explain, in concrete physical terms, what a measurement actually is, struck most of the field as a curiosity at best. It was in fact one of the most quietly important papers of the century, and its central idea is now called decoherence. Z's insight begins with something almost embarrassingly obvious, once it is pointed out. Nothing in the real world is ever isolated. A particle, an atom, a speck of dust, a coffee cup, any object you can name, is constantly being touched. Air molecules are striking it. Photons of light are scattering off its surface. Thermal radiation, the faint warmth that every object both emits and absorbs, is flowing in and out of it ceaselessly. And here is the key. Every one of those touches is itself a quantum interaction. Every air molecule that bounces off an object, every photon that scatters from it, becomes, in that instant, entangled with it. The object's quantum state and the environment's quantum state become correlated, linked, woven together. And when a quantum system becomes entangled with not one, not 10, but trillions upon trillions of environmental particles, something happens to the delicate property that makes interference possible. That property is called coherence, and it is, in essence, the precise phase relationship between the different parts of a superposition, the relationship that lets the two halves of a wave interfere. When the system entangles with its vast environment, that coherence does not vanish from the universe. It is not destroyed. It is spread. It leaks out, smeared across so many trillions of environmental particles, scattered into so many places at once, that it becomes, for all practical purposes, impossible to ever gather back up. The system stops looking like a quantum thing. It starts looking like an ordinary, classical, definite thing. Not because anything collapsed, because its coherence is now shared with the whole room, and the whole room is not going to give it back. A physicist named Wojciech Zurek, working at Los Alamos, took Z's idea and built it into a full framework through the 1980s. He gave us the concept of pointer states, the small set of stable, robust states that can survive constant battering by the environment, which is why we only ever see objects in those particular states, and not in bizarre smeared superpositions. And later he developed something he called quantum Darwinism, and the name is well chosen. In ordinary Darwinism, nature selects certain traits by copying them into the next generation. In quantum Darwinism, the environment selects certain states by copying information about them, over and over, redundantly, into the world around the object. Let me make that concrete, because it is the most important idea in this beat, and I want you to feel it, rather than just file it away. Let me put you in an ordinary room, slow time down, slow it right down, until you can almost see the individual events. There is a lamp in the room and a wooden table. Photons are streaming off that lamp, billions upon billions of them every second, and a great many of them are striking the table. And every photon that strikes the table and bounces away carries with it, imprinted in the way it scatters, a small copy of information about the table, where its surface is, its colour, its shape. And those photons fly off in every direction. Some of them, a tiny fraction, happen to enter your eye, and that is what you call seeing the table. But your eye was never special. The same information is being carried by millions of other photons going to every other corner of the room, and by the air molecules colliding with the table's surface billions of times each second, and by the faint thermal radiation the table itself gives off. The environment is making redundant copy after redundant copy of the table's state, and broadcasting them outward in all directions, constantly, ceaselessly. That is why you and another person, looking at the table from across the room, agree on what you see. You're not both looking at the table. You're each reading a different one of the countless copies of the table's state that the environment has already made. And this gives us finally a clean and physical answer to the question we have been circling all night. What is observation? An observation is this. It is any physical interaction in which information about a system becomes recorded in and copied into another system. That is all it is. It does not require a mind. It does not require life. It does not require awareness of any kind. When you place a detector at the slits of the double-slit experiment, the detector becomes entangled with the electron. The air around the detector becomes entangled with the detector, the thermal radiation becomes entangled with the air, and the electron's coherence, the information about which slit it took, diffuses out into the environment faster than thought, faster than you could possibly blink. The interference pattern dies, not because a conscious being looked, because the environment looked, the air in the laboratory looked, the thermal photons looked. Every physical system that became entangled with that electron's path is, in the only sense that matters, an observer, and there are trillions of them, and they are observing, all of them, all the time, and they do not need permission, and they do not need awareness, and they do not need to be alive. The numbers here are almost violent in their scale. For a single grain of dust floating in sunlight, the coherence between two slightly different possible positions is destroyed in something like 100 billionth of a second. A single photon bouncing off that dust grain is enough to do it. For an object the size of a bowling ball, the decoherence happens so fast there is barely a sensible way to write the number down. This is why you have never seen a chair in two places at once. Not because a chair is somehow too large for quantum mechanics to apply to it. Quantum mechanics applies to the chair perfectly well, governs every atom in it. But the chair is in contact with something on the order of a billion air molecules bathed in thermal radiation, exchanging information with its surroundings through billions of interactions every second. The environment is measuring the position of that chair constantly, redundantly, relentlessly. The chair's ability to be in a fuzzy superposition of places is destroyed before it can ever build up. The chair is in one definite place because the universe has already asked, "Where is the chair?" an unimaginable number of times before you ever opened your eyes. Your glance at the chair is not the observation that fixes it. Your glance is redundant. The environment got there first. The environment always gets there first. You live, in other words, inside a universe that is observing itself, everywhere, without pause, every atom measured by every photon that touches it, every molecule entangled with its neighbours, every surface quietly radiating information about itself into the dark. This is not a metaphor, and it is not mysticism. Zurek's quantum Darwinism has been tested. In 2019, an experiment using nitrogen vacancy centers in diamond watched quantum information from a system proliferate into an environment of nuclear spins, and confirmed that several independent observers could indeed each pick up a consistent copy of the system's state, exactly as the framework predicts. I find this idea, strangely, more calming than frightening, and I want to leave you with that, because the audience for a story like this is often listening late, drifting, and I do not want to hand you something jagged at this hour. The picture is not a cold one. It is a picture of a universe so saturated with this gentle, ceaseless mutual observation that reality is being continuously stabilized, continuously made definite by everything touching everything else. The moon is not uncertain. The moon is there in one place, solid and real, whether or not a single human being is awake to look at it, because trillions of photons and air molecules and gravitational interactions are touching it, reading it, recording it, every moment of every night. The universe does not need your attention to be real. It is holding itself together perfectly well without you. And there is, I think, a kind of peace available in that, if you let yourself feel it. You are not responsible for keeping reality switched on. But decoherence, for all its power, leaves one question open, and it is the question that carries us into the deepest part of tonight. Decoherence explains, beautifully, why the interference pattern disappears. It explains why we never see the chair smeared across two places. What it does not explain, what it cannot explain, is why you see one particular outcome. The branch where the electron went through slit A and the branch where it went through slit B, decoherence says, both still exist. They have simply lost the ability to interfere with each other. The universe, according to decoherence alone, has not actually picked one. You have experienced one. But the mathematics does not say the other was erased. And that gap, that quiet, stubborn gap between the disappearance of interference and the appearance of a single definite reality, is where the very last and strangest idea of the night is waiting. Let me stay inside that ordinary room a little longer, because I think the picture of decoherence is one of the genuinely beautiful ideas in physics, and it deserves more than a quick sketch. Slow everything down again. Slower this time. Slow it down until a single second stretches out into something you could walk through. In that stretched second, look at the wooden table, and try to count what is happening to it. The lamp is pouring photons onto its surface, and each photon, in the instant it touches the wood and scatters away, has become entangled with the table, has taken a copy of the table's state with it into the room. There are billions of those photons every second. And it is not only light. The air is not empty. The air is a crowd. Molecules of nitrogen and oxygen are colliding with the table's surface. Billions upon billions of collisions in that single stretched second. And every collision too is a quantum interaction. Every collision too leaves the air molecule carrying a faint record of where the table is. And the table itself, simply by being warmer than absolute zero, is glowing, very faintly, in infrared, radiating its own thermal photons outward, each of them another small messenger carrying another small copy of the table's state away into the world. You cannot see any of this. It is far too fast and far too small, but it is happening relentlessly every moment to every object around you and to you. And what it means is that the table's quantum coherence, its theoretical ability to be in a blurred superposition of slightly different positions, never has a chance. It is destroyed almost instantly, not by being annihilated, but by being copied, smeared, broadcast into so many photons and so many air molecules that gathering it back together would be more impossible than unscrambling an egg. The table is in one definite place because the room has already asked it, "Where are you?" an astronomical number of times, and the table has already answered, and every answer has been written down in a billion places at once. This is what observation actually is, stripped of all the mysticism. It is not a mind turning its attention towards something. It is the environment, ceaselessly, automatically, copying information about a system into itself. And it makes the question, who is the observer, almost dissolve, because the answer is everything. The answer is every photon, every molecule, every surface, every faint thread of radiation. The universe is wall to wall with observers, and not one of them needs to be awake. And so, when Einstein asked his famous, slightly mischievous question, "Do you really believe the moon is not there when nobody's looking at it?" the second layer of the double-slit experiment finally lets us answer him properly. The moon is there. Of course the moon is there. But the reason it is there, solid and definite and real in one particular place, has nothing whatsoever to do with whether a human being is awake on the night side of the Earth to glance up at it. The moon is there because it is drowning in observation. Sunlight is striking it and scattering off it, carrying copies of its state across the solar system. The faint pressure of starlight, the gravitational tug it trades with the Earth every second, the constant sleet of particles from the sun, all of it is reading the moon, recording the moon, fixing the moon in place. The moon is decohered into a single definite reality by its endless conversation with the rest of the universe. It does not need our minds to make it real. It needs information. And information is flowing between the moon and everything around it. every nanosecond of every night, whether one single conscious creature is paying attention or not. Part 11. It from bit. John Wheeler, looking back on his long life in physics, used to divide it into 3 periods. He described them with a kind of plain bluntness. The first period, he said, was everything is particles. That was the young Wheeler, working with Bohr on nuclear fission, working on the bomb, building a physics out of protons and neutrons and electrons, a world made of solid little pieces of stuff, and the job of the physicist was to find the rules that governed the stuff. The second period was everything is fields. That was the middle Wheeler, who turned to Einstein's general relativity, who came to see gravity not as a force but as the curvature of a field, who saw space-time itself as a physical, bendable thing, and who wondered whether particles themselves might be nothing more than knots and excitations in the geometry of those fields. It was during that period, by the way, that Wheeler coined the term black hole, because the older name, gravitationally completely collapsed object, was, in his words, not a name to inspire the imagination. But it is the third period that we have come here for, because the third period, the one Wheeler arrived at in the 1970s, and spent the rest of his life developing, was the most radical of the 3. The third period was everything is information. Wheeler captured it in 3 words, a phrase that has become quietly famous and is almost never properly explained. It from bit. And what he meant by it was this: every it, every particle, every field of force, even the fabric of space-time itself, derives its very existence, its function, its meaning from binary answers to yes or no questions, from bits, not bits in the sense of a computer's memory, bits in the sense of reality's bottom layer. Wheeler was making a genuinely astonishing claim, and I want to be sure you hear how astonishing it is. He was not saying that information is a useful way to describe the physical world. He was saying that information is the physical world, that the bit comes first and the it, the particle, the field, the substance, comes out of the bit. Information in this picture is not a description of reality. Information is what reality is made of. Wheeler loved to illustrate this with a parlour game, and I want to take you to the dinner party where he played it, because the story is the clearest window into the idea that anyone has ever offered. You know the ordinary game of 20 questions. One person thinks of an object, the others ask up to 20 yes or no questions and try to guess it. Wheeler describes arriving at a dinner party, and the game is proposed, and he is chosen to be the guesser. So he is sent out of the room, the way the rules require, while the other guests settle on an object for him to guess. He waits outside. It takes a while. Finally he is called back in, and he begins to ask his questions. Is it larger than a bread box? And there is a pause, a longer pause than there should be. Then, yes. Is it alive? Another pause, the guests glancing at one another. Then, no. And as the game goes on, Wheeler notices that every answer is coming slowly, that each person he asks seems to be thinking much harder than the simple question should require, and that the answers, while they keep coming, seem to be picking their way carefully forward. He narrows it down, question by question, and at last he takes his guess. Is it a cloud? And the room bursts out laughing, and then they tell him the secret. While he was waiting outside, the guests had agreed not to choose an object at all. Instead, they had agreed on a single rule. Each person, when asked a question, could answer however they liked, yes or no, freely, with only one constraint. Their answer had to remain consistent with every answer that had already been given. That is why the answers came slowly. Each guest, when their turn came, had to stop and check the whole history of the game so far and find an answer that did not contradict any of it. There was no cloud in that room when Wheeler began asking his questions. The cloud did not exist in advance. The cloud was brought into being, summoned, by the questions themselves. Each answer narrowed the space of what was still possible until, at the end, a definite object, a cloud, had been created by the accumulated yes and no, where at the start there had been nothing chosen at all. That, Wheeler argued, is what a quantum measurement is. A measurement is not the act of uncovering a fact that was already sitting there, fully formed, waiting to be found. A measurement is the act of asking a yes or no question, and the answer brings a fact into being. The photon in the double slit experiment does not have a definite path before the measurement asks which slit it went through. The measurement creates the path. The electron does not have a definite spin before the detector asks, up or down. The detector creates the spin. The physical world at its deepest level is not a collection of objects sitting there with pre-existing properties. It is a web of questions and answers, each answer constraining the next, each bit of information defining a small piece of reality that simply did not exist before the question was asked. And this is precisely why the consciousness story was always a distraction, a wrong turn. Because asking the question does not require a mind. A machine can ask the question. A quantum random number generator can ask the question. A photon glancing off a dust grain can ask the question. Any physical interaction that irreversibly records one bit of information about a quantum system is a measurement. It creates a fact. It brings an it out of a bit. The universe does not need a conscious being to ask its questions. It is asking them of itself constantly everywhere, through every physical interaction, trillions upon trillions of times each second in every cubic centimetre of space, building reality out of bits, one answer at a time. Wheeler was not alone in arriving here, and the company he keeps should make you take this seriously, rather than dismiss it as the poetry of an old man. Anton Zeilinger, the same Zeilinger whose Vienna group ran the entanglement swapping experiments and who would go on to share the 2022 Nobel Prize in Physics, proposed something he considered the most basic principle underlying quantum mechanics. An elementary system, Zeilinger said, carries exactly one bit of information, one particle, one bit. That is all it can hold. If you measure a particle's spin, you have spent its bit. It gives you a clean, definite answer, up or down. But now it has nothing left to give. Its position, its momentum, every other property becomes maximally uncertain. Not because you disturbed it with a clumsy instrument, but because it only ever had one bit to offer in the first place. And if that is right, then it is the deepest explanation anyone has ever given for why the double-slit experiment behaves the way it does. The electron can show you an interference pattern, or it can show you which slit it went through. It cannot show you both, and the reason is not a limitation of your equipment, and it is not the uncertainty principle applied to your detector. The reason is that the electron does not contain enough information to answer both questions at once. One bit, one answer. You choose which question to ask, and the answer you get back is the reality that gets created. Ask which slit, and you bring a particle into being. Ask what pattern, and you bring a wave into being. The electron is not being coy with you. It is not hiding a complete set of facts behind a curtain. It genuinely does not possess a fact about its path, and a fact about its interference at the same time. The fact does not exist until the question that creates it is asked. In his Nobel lecture in 2022, accepting the highest honour his field can give, Zeilinger said that physics may need a unification of the two concepts of reality and information, that the distinction we casually draw between the world, on the one hand, and the data about the world on the other, may turn out not to exist, that the it and the bit may not be two things at all. They may be one thing, and if they are one thing, then everything you imagine the universe is fundamentally built out of, matter, energy, particles, fields, is not the bottom floor. The bottom floor is bits. Answers to yes or no questions, information with nothing underneath it, a record with no substance it is written on. And that, finally, is the doorway to the last thing I have to tell you tonight. Part 12. The record that needs no reader. Let us go back, now, to the very beginning. Back to a room in London in 1803, and to Thomas Young standing in front of a wall with a sunbeam and a thin card, watching bright bands and dark bands appear, and feeling certain that he had just settled once and for all the question of what light is. Young thought he was discovering that light is a wave, and he was. But he was also doing something larger than that, something he had no language for and could not have known he was doing. He was discovering that the behaviour of light depends on the structure of the information available about it. Two beams overlapping, with no way to tell which photon came from which side of the card, produce interference. Block one beam, make the path knowable, and the interference vanishes. From the very first day, from that very first card on that very first wall, this experiment was always about information. Young could not say so. Bohr, a century later, would dance around it with his principle of complementarity. Heisenberg would half bury it under the uncertainty principle. Copenhagen would hide the question under a cup and declare the game finished. But the answer was always sitting there, underneath all of it, waiting. information. And here is the thing I asked you to carry all the way from part 2, and I hope you have kept it. The experiment never changed. Think about that across the whole 220-year span we have just walked. Young's sunbeam, Jansen's stripes emerging in a Tübingen basement, Tonomura's 70,000 dots resolving out of static, Kim's coincidence counts, Zeilinger's entangled photons crossing 144 kilometers of open air between two islands. It was, in every meaningful sense, the same experiment, asking the same question, giving the same answer the entire time. The apparatus got finer, the particles got lonelier, fired one at a time instead of in beams. The choices got faster and moved out of human hands into machines, and then into machines so far apart that not even light could connect them. But the experiment itself never changed. What changed, slowly, painfully across 2 centuries, was only ever our ability to hear what it was saying. The experiment never changed, only our ability to hear it. And now, at last, we can say plainly what it has been saying all along. The behavior of reality, whether a particle spreads out as a wave or commits to a single path, is determined not by what you know, and not by what you observe, and not by whether you are conscious or alive or capable of any experience at all. It is determined by the structure of information itself, by whether a record exists, anywhere, in any form, encoded in the state of any system at all, a detector, a stray atom, a passing photon, the warmth of the air, read or unread, examined or abandoned, known to someone or known to no one. The universe is not watching itself through your eyes. It never was. The universe is writing itself into being through the existence of bits, through the laying down of records, and a record does not need anyone to read it. That phrase has been with us since part 5, and now you can feel the full size of it. A record does not need anyone to read it. It does not need a mind to write it, and it does not need a mind to read it, and it does not need anything to be written on. The universe responds to the existence of a record the way it responds to nothing else, and the record asks for no audience. I told you near the start of tonight that the double slit experiment has a second layer, and that the second layer is worse than the first. We have arrived at the place where I can finally tell you what that word, worse, was always going to mean. It never meant frightening. I promised you that, gently, at the beginning, and I have tried to keep the promise all the way through. Worse meant stranger. Worse meant more impersonal. The first layer, the comfortable one, the spooky one, kept us at the centre. It said the universe responds to observation, and it let us quietly assume that observation meant us, our awareness, our looking. That was the warm version. That was the version that made us matter. The second layer takes that away, and what it leaves in its place is colder in one sense and, I would argue, vaster in another. The second layer says the universe was never responding to us. It was responding to information, to records, to bits. We were never the observer it was waiting for because it was never waiting for an observer at all. It was only ever waiting for a question to be asked, and the universe asks itself those questions, ceaselessly, everywhere, with or without anything alive to care. And here is the part that I think is genuinely worth sitting with, in the quiet, before you sleep. There is a way to feel that as a loss, and I will not tell you the loss is not real. We do not get to be the special ingredient. The cosmos does not lean in to notice us. But there is another way to feel it, and I think it is the truer way. You're not the audience of reality watching it from some seat outside. You're not separate from the record. You're part of it. Every atom in your body is being read, right now, by the photons and the air and the gentle radiation around you. You're one more place where the universe is keeping its record of itself. You're not outside the experiment looking in. You're inside it, made of the same bits as everything else. One more it brought into being by one more bit. That is not a small thing to be. It might, in fact, be the largest thing there is. So what is the record made of? That is the question I have to leave in your hands, because it is the question physics itself cannot yet answer. Wheeler spent the last 30 years of his life on it, running at it the way, by every account, he ran at everything, charging down stairwells well into his 90s, hooking his arm around the banister for speed, racing ahead of much younger visitors to be the one who held the door open. He spent those decades trying to say what information, at the bottom of everything, actually is. He did not solve it. He never expected to. He once said that his greatest ambition was simply to understand how come existence, and he knew he would not reach it. Zeilinger, accepting the Nobel Prize, could only say that reality and information may need to be unified, and could not say how. Nobody can say how. As of tonight, as of this exact moment, physics knows that the universe responds to the existence of a record, and physics cannot tell you what the record is written in. That is a real mystery, not a solved one dressed up to sound open, a genuinely currently tonight unsolved one, and I think that is the right place to leave you, not with an answer tied in a bow, but with a true question held lightly in the dark. The double slit experiment has been pointing at this since a Quaker prodigy split a sunbeam with a card. The experiment never changed. We are only now, slowly, learning to hear it, and what it is telling us, patiently, across 2 centuries of finer and finer machines, is that reality is not made of stuff. It is made of answers. It is made of a record that writes itself and needs no one to read it, and somewhere underneath that record is the last question, the one Wheeler died still running toward, the one nobody has reached. What is it made of? The universe is keeping its answer. And for now, on this quiet night, it has not yet been asked in the way that would bring that final answer into being. Good night, and thank you for following the thread this far into the dark.